Hi, in this video we're going to look at another distributed load example. So I have drawn this already, and if you are copying down your notes, so you can pause and redraw this. And one thing I want to mention, this curve is power of 2 parabola x square. All right, so a quick review. How do we solve distributed load? We're going to substitute it with a concentrated load. And in order to do that, we need to know the magnitude, which is area underneath the curve. So for this situation, will be area underneath power of 2. And also we need to locate this load, which is at the centroid of this curve. All right, in order to do that, what I'm going to do is I'm going to draw my new FBD on the top of this original one. A is pin support, so what do we have? We'll have AX and AY. For B, it's here I'm going to particularly mention it. This is going to be on a frictionless surface. What does that mean? It means it can move freely at E horizontally. So only force we have is just E at the Y direction. So we call that E. Okay, get rid of the subscript EY. Those are the three unknowns you are solving. Again, the goal for this reload is trying to find those reaction support. You're finding AX, AY, and E. So how do we replace this reload with one single concentrated load? For here, you can we again review if it's power of 2, the area we talked about in one video, it's going to be, this entire beam is 12 meter because it's a 6 meter plus 6 meter, 12 meter. And this height is 3 kilonewton per meter. And we know for parabola, the area is going to be 1/3 base times height. That would give us 12 kilonewton, all right? And in terms of the centroid of it, and the centroid for this power of 2 is going to be, we learned it's going to be at 1/4, right? So if you're not familiar with this, go back to look at one of the videos. It's about centroid for common shapes and the core pattern. So in that situation, if this is a C, this is a A, and this concentrated load will be 1/4 of 12. That will give us 3 meter from point C. Right, so now let's go ahead, draw that equivalent concentrated load would be somewhere here with magnitude of 12 kilonewton. That's the area, and it's going to be 3 meter from C. Okay, now don't forget on this FBD, we still have forces at D horizontally. We still have this external moment at B with 18 kilonewton meter. That's the moment unit. So knowing that, we're going to, I think we're ready to construct our equilibrium equation. Forces at the X direction. What do we have here? We have AX at the X direction, and we'll have D at 20. We also know this D, actually, I'm going to replace that. That's going to be 20 kilonewton to the right, plus 20. That equals 0. Force at Y, what do we have? We'll have AY. And then we'll have negative 12 kilonewton, that's going downward. Then we'll have this E, that's going up. That equals 0. So those are the three forces. Now we're going to look at the moment. The moment we're going to choose where you have several things going on, which is point A, since have AX and AY. Then in this moment equation, we're going to include our 18 kilonewton meter because that's external moment. And be aware, do not put this 18 kilonewton meter, this moment, into force at X or Y, because that's totally different unit. So here 18 kilonewton, look at it, it's going what? Going counterclockwise, so that's going to be positive. Then we'll have this external moment, this equivalent concentrated force 12 kilonewton and rotating about A. So the moment of arm is going to be from here to here. That's moment of arm. And knowing this entire one is 12 meter and it's -3 from C, so it will be 9. And that force rotating about A is clockwise, so it's going to be negative. Then we're going to look at this 20 kilonewton. What's the moment of arm rotating about A? So rotating about A, this force is X direction, so the moment of arm is going to be Y direction. And it would be that question mark there, and that's 2 meter. And this force rotating about A is going to be counterclockwise, so that would be positive. Okay? Now, the last thing we're going to have is this point E. This E is going to rotating about A. Then the moment of arm is going to be this entire horizontal length. We'll have 6 plus 6 plus A. And that's counterclockwise, so it's going to be positive. All those equal to 0. Okay, so in that situation, again, if you look at equation number 3, the moment equation, you can figure out the unknown E in one step, right? So let's go ahead and simplify that. So we have 18 minus 12 times 9 here, so that'd be 108. Then plus 40, then plus this 12 plus 8 would be 20E, that equals 0. Then we can go ahead and solve. Our 20E is going to be 108 minus 40 minus 18, and I think that's going to give us 60. Nope, that's going to give us 50, I think. Okay, then we can solve our E, will be 2.5, and the unit will be 2.5 kilonewton. Okay, now once we solve E, we can bring up to the equation number 2. Then we can solve our AY. Our AY will be 12 minus E, which will be 12 minus 2.5. That will give us 9.5 kilonewton. Then from equation number 1, we can go ahead and solve AX in one step. That's equal to negative 20 kilonewton. So those are our answer. All this tells us is, which means this AX being negative, it just means we guessed wrong initially. However, don't need to go ahead and change the direction on your FBD. It just means AX true direction is pulling to the left. Okay, so this is a quick example on distributed load. And this example we see, I see a couple of things that's worth to pay attention. The first one is this external moment, 18 kilonewton meter. Make sure it showed up in your moment equation right there. And also is when you have this parabola, use those common shape pattern. The area is going to be 1/3 and the central is going to be 1/4. And again, for different power, there's a formula for that. So go ahead and review that one if it needs to be reviewed. All right, I'll see you next time. Bye.